Okay, so ladies and gentlemen, you are welcome. So in today's video, we are going to look at the solution to past question paper in Chem 101, that is general chemistry. So let's start with question 1. So the question says, according to Avogadro's hypothesis, the volume of solid and liquid are considered to be dash 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 A 0, B 1, C 2, D 273. So actually, Avogadro's hypothesis or Avogadro's law is a law that states that the equal volume of all gases under the same temperature and pressure contain the same number of molecules. Like for example, let's see, you have methane here as gas reacts with oxygen to generate CO2 plus water molecule. So let's say the gas of CO2 is, sorry, the molecules of CO2 here, let's say is 0.5 mole. So that is 0.5 mole, here is 0.5 mole. So, okay, or let me just write it here, 0.5 mole. So you can see clearly the number of moles of CO2 here is 1 mole. And then the number of molecules of CH4 is also 1 mole. So all these, there are gases. This one is also gas. So now, already the number of moles of CO2 here is already given as 0.5 mole. So 1 mole is equivalent to 1 volume of CO2, and 1 mole of CH4 is also equivalent to 1 volume. So the equal volume of all gases under the same temperature also contain the same number of molecules. So if the volume of CO2 here is 1 mole, and the volume of CH4 is 1 volume, then if the volume, or if the number of molecules of CO2 is 0.5 mole, then the molecules of CH4 is also going to be 0.5 moles, because they contain the same number, or they contain equal volume. So Avogadro's law is only applied to gaseous molecules. It's only applied to gaseous molecules. It doesn't apply to solids, and it also doesn't apply to liquids. So if it is actually on a solid and liquid, so the Avogadro's law is equal to 0. So therefore, the answer to this is 0, because here is a solid and liquids. If it is for actually a gaseous molecules, then it's not going to be equals to 0. You will use the equation to actually get the volumes. Like for example, here we have 1 moles of CH4 and we have 1 moles of CO2. So the volume is equal to be 1 volume, 1 volume. So if the gaseous molecules contain the same molecules, then it means that they are going to have the same volume. So therefore, because here the phase of the molecules is solid and liquid, so Avogadro's law, it doesn't apply, and that is why the answer is E. So then calculate the volume of 22 gram of ammonia at STP. So how do we calculate this? It's simple. So we said ammonia is CH3. So ammonia is CH3. And of course, how many nitrogen do we have here is 1. Then times the mass of nitrogen is 14. So we have 1 times 14. Then we put it in bracket. Then plus hydrogen. So we have 3 hydrogen. So we now say 3 times. The mass of hydrogen is 1, so we have 1. Then we put everything in brackets. So we now have 1 times 14 is equal to 14, plus 1 times 3 is equal to 3. And this will give us 17 gram per mole. So this is the number of molecules of methane, sorry, of the ammonia. So then now the next thing that we are going to do here is to calculate the mole, So mole is equal to, of course, mass. Mole is equal to mass all over molar mass. So the mass is 22.5 divided by 17. So now when we check our calculator and we now say 22 22.5 divided by 17. That will give us equals to, the mole is now going to be 1.32 mole. So we have 1.32 mole. But the question is actually asking us to calculate the volume at STP. So there's also a formula that says mole, which is N is mole, is equal to volume all over 22.4 dm cube. All over 22.4 dm cube. So now we have our mole as 1.32. So we have 1.32, then it's equal to volume divided by 22.4 dm cube. So we are now going to make the volume subject of the formula. So we now have volume by cross multiplication. We now have 1.32. We have now 1.32 times 22.4 dm cube. So we now press our calculator by saying 1.32 times 22.4. So at the end, when we calculate this, then this one actually it gives us a total of 29.568 dm cube. So this is what we're supposed to actually get from this calculation. So we have the mass of ammonia is 17, and sorry, the molar mass of ammonia is 17, and then the mass is 22. Sorry, the mass is 22.5. So we now set mass divided by molar mass. So we have 22.5 divided by 17, and that gives us 1.32. So we have 22.5 divided by 17, and that gives us 1.32. Then we now multiply it with 22.4 dm cube. So the answer is supposed to be 29.568 dm cube, but the answer is not given here. So this is how to follow the steps and do the calculation. So then now, question 3. In the oil drop experiment, Millikan determined the A, mass of electron. But okay, let me also ask you, do you think there is any other way that you can solve this question and get the answer? If yes, please do it, and please put the answer on the comment section of this video. So then now in the oil drop experiment, Millikan determine A, mass of electron, B, charge of electrons, C, charge to mass ratio of electrons, then D, mass of the proton. So the answer is B. So Robert R.A. Millikan, or Robert A. Millikan, is a scientist that was able to discover the charge of electrons, which is negative charge. So he's the scientist that was able to discover the charge of electrons, while we also have a scientist called J.J. Thomson, which is actually the scientist that was able to discover the electron itself. James Chadwick discover neutron, and then of course the R.A. Millikan discovered the negative charge, while the protons, which is the positive charge of the electrons, it also. So this is actually the discovery of Robert R.A. Millikan, which is the scientist that was able to demonstrate that the electrons is negative charge. So meaning that he is a scientist that actually discovered the negative charge of electron. So then, which of the following is a mixture? So when we said a mixture, is when we have two or more substances that are physically combined together. So A, we have seawater, B, we have iron filling, C, we have sodium chloride, and D, we have granulated sugar. So the answer is actually seawater, because most of the seawater, they contain salt. They are salty water. So it means that they contain water, they contain salt in them, and many other substances. So So that is why seawater is an example of mixture. So now the following equation below is an example of, so you see, if you can look at the equation here, you have uranium. So the uranium is uranium 238, and then the atomic number here is 92. So it breaks down to produce thorium 234, and then we have 90 here plus helium. Here is 4 and here is 2. So this equation is an example of A, artificial radioactivity, B, natural radioactivity, C, nuclear transmutation, D, nuclear reactor. So you see, if you can look at this reaction, it is a reaction that when it is on, spontaneously disintegrate to produce thorium and helium. So this means that it is natural radioactivity. Because it is on, it doesn't actually bombarded by any particles before they undergo the disintegration. So it means that they are natural radioactivity because they are originally unstable. So they disintegrate, they break down to fragment and generate other heavy nuclear atom. So you see, in this case, there is no any high particles or high charge particles, and there is no any heavy particles like protons, neutrons that are actually used to bombard the uranium it to undergo the radioactivity. So you see, it is on because it has unstable nucleus. That is why it breaks down to produce other radioactive substances. So it is natural radioactivity. So the answer is natural radioactivity. So then another question is, what quantity of electricity is required to deposit 9.0 gram of aluminium from its salts? For aluminium, of course, let's say this is the aluminium. So usually the aluminium dissociates to produce aluminium 3 plus. Then at the end, 3 electrons will be used to make this aluminium neutral. So it means that here we have, of course, 3 Faradays. So how do we now calculate the quantity of electricity in this case? So of course, we know that the mass of aluminium is 27 grams. So we can say now 3 Faraday is equivalent to 27 gram. And then we have, of course, because what we want to get is the quantity of electricity, that is the number of Faraday. So we can now say Q is present in, of course, how many gram? 9.0 gram. So we now cross multiply. So we now have Q is equal to 3 Faraday times 9.0 divided by 27. Then at the end, we have, when we multiply 3 times 9 is going to give us 27F divided by 27. So 27 divided by 27 is going to give us 1. So that is why we have 1 Faraday. So the answer to this is 1 Faraday. So 1 Faraday is the answer. So don't forget, ladies and gentlemen, this is how to do calculation in electrolysis. And I have videos for this, or for how to, or on how to calculate, how to do calculation in electrolysis. And I will attach the link to this video so you can find it on the description box if you want to watch the video on how to calculate electrolysis. So then the answer is 1F, as you can see clearly from here. So then we have another example here. The question says, we have another question here, which is number 7. The question says the half-life of cobalt is 5.26. So the half-life is equals to 5.26 years. If 50 grams are left after 15.78 years, so it means that the mass remain, MR, that is mass remain, is equal to, the mass remain is equal to 50 gram. Then this 50 gram is left after 15.78 years. So it means that the period of this radioactive decay is 15.78 years. Yes, this one also yes. Then how many grams are in the original mass? So we want to get the mass of original mass, that is MO. So how do we do that? There is a formula that says mass remaining is equal to original mass divided by 2 power n. So what are you going to do now is to calculate the power n. Sorry, is to calculate this n here, and then we use it to calculate the original mass, which is unknown. So how do we do that? N, it means the number of the half-life undergoes by a particular radioactive substances. So to do that, you just take a ratio by saying period of the decay divided by the half-life. So you see the period of the decay, that is the number of years covered by the radioactive substance, is 15.78, and then 15.78, and then you now divide it by the half-life, which is 5.26. So if you now take 15.78 divided by 5.26, is going to give us 3. So it's here for us to calculate the original mass. We are now going to see the mass remaining. So we already know that, okay, the mass remaining is 50 grams. Then it's equal to original mass divided by 2. Then our n is equal to 3. So we are now going to say 2 power 3. So we're now going to cross multiply this time this. Then we now have original mass is equal to 50 times 8. So this will give us original mass is equal to 400 grams. So let's see. It means that the answer is A. The answer is A, 400 grams. So let's look at question 8. Here we have 80 grams of AU with a mass of 98 decays to 6.25 grams in 10 days. What is the half-life? So you see, in this case, we want to get the half-life. So already here, we are given the original mass and the mass remaining. So we are also going to apply the same formula. The mass remaining is equal to original mass divided by 2 power n. So you see here we don't have 2 power n. So what we are going to do now, the mass remaining, which is 6.25, is equal to the original mass is 100 divided by 2 power n. So we make 2 power n subject of the formula. So therefore, we now have 2 power n is equal to 100 divided by 6.25. So how do we do that now? We are now going to say 100. We are now going to say 100 divided by 6.25. And that gives us 16. It gives us 16. And don't forget that 16 is the same thing as 2 power 4. So therefore, you can now say 2 power n is equal to 2 power 4. So therefore, this 2 will now take care of this 2. Then we now have n is equal to 4. So we now have n is equal to 4. So now how do we calculate the half-life? Then we now use the formula which says n is equal to period divided by the half-life. So you see the period here is 10.8 days. So we can now make T half subject of the formula, that is the half-life. Subject of the formula then is equal to period. The period is 10.8 days, then divided by the n. So n is equal to 4. So we are now going to have half-life is equal to 10.8 divided by 4. And that gives us 2.7. That gives us 2.7 days. So it means that the half-life of AU element here is 2.7 days, which is something as 2.67 days. So this is the answer. This is just like an approximation. So we have 2.67 days. So then the next thing is identify X in the nuclear reaction below. So we have the following. So what is X? So I think it's simple. We start with the products. We start with the mass of the element. So you see the mass of the element first is 235 plus the mass of the element. Here we can now say A. Here we can now say B so that we can get the values from there. So we have 235 plus here is 0, then it's equal to 148 plus 85, then plus 8. So we can now say 235 is equal to, so we can now say 148, because at the end, the mass of the reactant is going to be the mass of the products. So we now have plus 85, so we have 233. So we now have 233. So we now have 233. So 235, we have 148 plus 85. So that gives us 238 plus A. So we can now make A subject of the formula. So you can now say 235 minus 233 is equal to A. So at the end, we have 2. So A is equal to 2. So I think, ladies and gentlemen, clearly if you can check on the questions, okay, we have 235, we have, oh, sorry, I think the mass of the neutron here is supposed to be 1. Here is supposed to be 1, and here, this is where it's supposed to be 0. So we have N here. We have N is equal to, here is 1, and here is 0. So instead of saying 0 here, we have 1. So therefore, it's 36 is 236. So we have 236 here minus 233. Then here we are going to have 3. And then here we have 0. We have 0. So we can now see on the for the atomic number. So we have 92 plus 0 is equal to 57. 57 plus 35 plus A. So let's see here. We have 92. Here is 92 plus 0. So we have 92 is equal to 57 plus 35. Then we have 92 plus A. So therefore, the plus B is not A, plus B. So B now is equal to 0. So now, what is the answer? So you see the answer here is going to be A, because here we have 3. So if we now say 3 times 1, it's going to give us 3. And if you say 3 times 0, it's going to give us 0. So therefore, at the end, the mass missing on the product side is 3. And then the atomic number is actually 0 for this B. So that means that the answer is A. So it means that it is 3 neutrons that are generated after the bombardment of uranium-235 with 1 neutron. So this is actually a typical examples of artificial radioactivity. You can see that in this case, the element, which is uranium-235, is stable. So it's now bombarded with 1 neutrons and 3 neutrons are generated. So then now, the stable nuclei have neutrons to protons ratio between 1 to 1.5, option A. Sorry, option C. Option A, 2 to 2.5. Option B, 1.6 to 2.0. Option D, 2.6 to 3.0. So what is the answer here? This one is also very simple. So generally, how do we know that the nuclei is unstable? So whenever the neutrons to protons ratio is less than 1, it means that that element is radioactive. Or when the neutrons to protons ratio is greater than 1.5. So whenever the neutrons to protons ratio is greater than 1.5 or less than 1, it means that that element is unstable. The nuclei of that element is unstable, meaning that it can undergo radioactivity. But when the value is between 1 to 1.5, it means that the nuclei is stable, indicating that that element is non-radioactive. So the answer is option C, 1 to 1.5. So any element that after you calculate its neutrons to protons ratio and you realize that the neutrons to protons ratio is between 1 to 5.1, it means that that element is not radioactive. Like for example now, let me just give example. Sodium has a mass number of 23, an atomic number 11, and of course it means that the proton here is 11, and then the neutrons number is going to be 12, because if you want to get the neutrons, we are now going to say 23 divided by, 23 minus 11. So that is where we have 12. So we now have neutrons, we have protons. So the neutrons is 12 and the protons is 11. So you can now say 12 divided by 11. So we now have 12 divided by 11, and that will give us 1.09. So you can see clearly this value is between 1 to 1.5. So it means that this 1.09 from sodium, indicating that the sodium is not radioactive element. Okay, then the next thing is alpha decay. So alpha decay is dissociated with isotopes that have atomic number A less than 58, B greater than 58, C less than 58, D greater than 83. So actually any element that have isotopes greater than 83, it means that that element is a radioactive element. It can also undergo alpha decay. So the answer is D. So two radioactive elements, P and Q, have isotopes of 120 and 3600 respectively. So which of the following element is more stable? So generally, ladies and gentlemen, the higher the half-life, the more stability or the more stable the atom is. So you can now go in to look at that. Okay, we have P and Q. So P has 1200 seconds, while Q has 3600 seconds. So it means that Q have the highest half-life, indicating that it is more stable than P. They are all unstable because they have half-life, so they can disintegrate to half of their original mass. But the one with the higher half-life, it means that it is more stable than that of the element with lower half-life. So the answer here is Q. So then radioactive particles can be detected using, so we have ways that we can generate or that we can detect radioactive substances. So detection of radioactive substances, number one, you can use scintillation counter, photographic plates. You can also use the diffusion cloud chamber, but X-ray diffraction method is not one of the method for detecting radioactive substances. So the answer is X-ray diffraction. So then now, nuclear fission is used in making A, hydrogen bomb, B, atomic bomb, C, pent, D, cables. So nuclear fission is actually, it has so many applications, but one of its major application is used in producing or in making atomic bomb. So the answer is D. 15. The modern theory which is used in the calculation of the region where electrons is probably located is known as A, Bose theory, B, quantum mechanics, C, uncertainty principle, D, Newtonian mechanics. So the answer is actually quantum mechanism or quantum mechanics. So a quantum mechanics is a modern theory that use in the calculation of the origin where electron is probably located. So that actually described as quantum mechanics. You know that there is actually what you call a Heisenberg of uncertainty principle, where he stated that the electrons as well as the momentum and the position of the electrons cannot be determined simultaneously. So, but in the quantum mechanics is a mechanics that's trying to actually use a calculation to determine the region or the area where electrons is probably located. So then the answer is quantum mechanics in this uh, question. So quantum mechanics is a mechanics that use a calculation in order to locate the region or where or the probability that are used to indicate where the location is probably located. So then the degenerate orbitals have the same values of quantum numbers. A, principal and magnetic. B, principal and spin. B, principal and azimuthal. D, magnetic and spin. So let's now take examples of some orbitals that have yeah some degenerate orbitals. So P is degenerate orbitals, D is degenerate orbitals. So you know that in hybridization, in orbit, we have four major orbitals: S, P, D, F. So P, D, and F, they are degenerate orbitals because they can be split in the magnetic field. So now, how do we do that? How do we do that? Let me just give an example. Let's say we have three P orbitals. So now that three P orbitals can be further split into three Px, three Py, and 3pz. So let's say here there is one electron and here there is also one electron. Here there is also one electron. So now if you ask, what is the energy level of Px? N is 3. It means that the principal quantum number is 3. Then also for the Py, the principal quantum number is 3. Pz is also 3. But what about the L? L, when L is equal to 1, so it means that the orbital is P. So you see, this one is also 1, this one is also 1. So you can see that the Px, the Py, and the Pz, they have the same principal and azimuthal quantum number. So the answer is principal and azimuthal quantum number. The set of four quantum numbers for an electrons in 3px1. 3px1. So how do you indicate the quantum numbers of these electrons? So it's simple. Remember, as I said, we have, and don't forget, if you actually didn't watch my video on quantum numbers, please go and watch it. It will really also help you. So this is 3p, because we said x, so this is 3px1. So it means that the electron is here. So how did we know the quantum numbers of this electron, this one electron? Is simple. So as we can see, the energy level here, the energy level, which is n, is equal to 3. And of course, remember, if the orbital is p, so whenever you have p orbitals, it means that you have L equals to 1. And then for the magnetic quantum number, remember that magnetic quantum numbers has a value of minus L, 0 to plus L. 2 plus L. So now, since L here is 1, so it means that the value of magnetic quantum number is going to be minus 1, 0, and plus 1. So it means that here we have minus 1, here we have 0, and here we have plus 1. So the Px have minus 1, the Py have 0, the Pz have plus 1. So it means that n is equal to 3, L is equal to 1. Then for the magnetic quantum number, which is Ml, is going to be minus 1. And for the spin, because it's actually looking towards the clockwise direction, that means that S is equal to plus half. So the answer here is option E. So the answer is E. So then the last, which is not actually the least, is how to calculate the wavelength of the phase line in the Balmer series of the spectrum of hydrogen atoms. So this is also very simple. So if you want to calculate the wavelength, we are now going to say 1 all over lambda is equal to Riemann constant is with open bracket 1 all over n1 square here is square minus 1 all over n2 square. So in the Balmer series, n1 is equal to 2 and n2 is equal to 3. So in the Balmer series, this is actually the value of n1 and n2. So we are already given Riemann constant in per centimeter. So we can now say 1 all over lambda is equal to the Riemann constant is, of course, 109,677, then divided by 1 all over. So n1 is 2, so 1 over 2 square minus 1 all over 3 square. So how do we do it? We are now going to say 1 all over lambda is equal to 10,9,677. 10,9,677 is equal to 1 all over 4 minus 1 all over 9. Then at the end, to calculate this, we are now going to have, of course, 10,9,677. Here is 7, then it's now equals to 9. Sorry, you don't need to put equals to. So now going to be 9 minus 4 divided by 4 times 9. So you multiply 4 times 9. What are you going to get? 4 times 9, we have 36. So meaning that at the end, we are now going to have 9 minus 4 is 5. So 9 minus 4 is 5. So we are now going to multiply with 109,677. So therefore, after we do that, then it gave us, it's now going to be 1 all over lambda. 1 all over lambda is equal to 4, sorry, 5, 4, 8, 3, 8, 5 divided by 36. So this is what we are going to have. So you can now take the reciprocal by saying lambda over 1 is equal to 36 divided by 548,385. So we can now see 36 divided by 548,385. So after you calculate this, it is going to give us this answer. So the answer to this, you know that in the hydrogen or in the spectrum of hydrogen, we have Lehman series, Valmer series, Pippon series, and fission series. So it is very, very important if you want to know this or how to do this calculation, you should go and to the hydrogen spectrum to get the value, so the n value of each of the series. For the Balmer series, for the Pippon series, for the fission series, you should go and follow them one after the other in order for you to get the value of n1, n2. So for the Balmer series, n1 is 2 and n2 is equal to 3. And that is why at the end, after making all this calculation, we get B as our answer. So ladies and gentlemen, please If this is the first time you come to my YouTube channel, please try to subscribe and join the YouTube community. So this is just only 18 questions. So I hope you will enjoy them, and don't forget to subscribe and join the YouTube community. So to join this YouTube community, you actually pay a total of 750 naira using your ATM, and I hope that a lot of questions will come from this of my YouTube channel, especially for Chem 101, Physics 131, Chem 121, and Biol 113. So don't forget to join and subscribe to the YouTube community. See you next in my next